Let's imagine someone showed us this graph, and let's say they told us this is a function. And let's say they told us that yet again they went to a town with a library and they asked the librarian, what will the late fees be for different, for however many days overdue our book is, what will the late fee be? So let's say this is a late fee function again. It's going to depend on how many days overdue the book is. That's the independent variable. And the answer or the result of the independent variable will be how much money you have to pay in a fine. That's the dependent variable. So let's say this guy went over to the neighboring library, asked the librarian the information, and made up this graph and came and showed it to us. And he said, hey, look, this is a function. The independent variable is the number of days overdue. The dependent variable is the fine. And I got an input, I got an output, I got data points. This is a function, according to this guy who's talking to us right now. What would we tell him? Well, we'd look at this function, and we'd look at something very important. We would look at this part of the function. His so-called function tells us that, okay, an input of 1 corresponds to an output of 1. An input of 2 corresponds to an output of 2. If we look over here, it looks like an input of 5 corresponds to an output of 6. That's okay so far, but look right here. This graph is telling us that if it's a function, an input of 3 corresponds to an output of 3 and an output of 4. This is saying that an input of 3 corresponds to an output of 3 and 4. Does that make sense? Does it make sense logically? Does it make sense that if you went and asked the librarian, hey, what will be my fine if my book is overdue by 3 days, and she told you $3 and $4? That wouldn't make sense, right? That's why we have that very important rule, defining functions really, that tell us that an individual input can only have one output. And if you have some relationship or graph written down where one of the inputs has multiple outputs, guess what? This is not a function. And we can recognize that visually very easily, or we can recognize it by looking at ordered pairs. Say we were given this function also, and this is, let's not say function, let's say we were given this graph also, and this graph purports to be or claims to be a function that describes the relationship, again, between the miles someone is from Philadelphia and the time it would take them to travel to Philadelphia. And as usual, miles from Philadelphia would be the input, time to travel to Philadelphia would be the output. So the axes are labeled correctly, and it looks like he has a smooth curve. So it is a continuous function. Sorry, it's a continuous graph as we would expect. But is it a function? Well, let's look at this point right here. Why does this point let us know that this is not a function? How can we figure it out? Sorry, not point, but this region. How can we figure out that this region lets us know that this is not a function? Well, let's take a look at what a input would be right around here. Let's say this was an input of, I don't know, 64 miles, okay? And what would the output be? Well, according to this graph, an input of 64 miles would have, look at that, 3 different outputs, right? It would have this output here, right? And I know I'm not being exactly neatest in drawing my lines, but I hope you get the picture. This graph purports that if this were a function, the input of 64 would have 3 outputs. And what do we know about a function? We know that an input must have exactly, I shouldn't say exactly, an input must have only one output, right? But here, this graph tells us that a given input has 3 outputs. So it's a graph, all right, because basically anything you can draw is a graph, but it's not the graph of a function. Let's take a look at something. Let's take a look at another graph. And I'm not going to really label the axes right now. I'm going to be pretty abstract. I'm going to just say we have this graph, and I'm going to say it looked like this, okay? So there's a very popular rule that you may have even heard before that can be used to determine whether or not a given graph is a function. And you might already know what I'm getting at, but this rule is called the vertical line test. Okay? And what is the vertical line test? The vertical line test says if you have a graph, and if that graph is a function, then a vertical line, a line that goes up and down, will only ever cross the graph once. Okay? But let's look at this graph that I've just drawn. If I place a vertical line right here, where did it? I didn't want that. If I place a graph right here, and it crosses the graph, the vertical line crosses the graph at 3 places, right? If I place a line right here, right, well, how many times does this vertical line cross the graph or intersect the graph? It still intersects it 3 times in this case, right? So that's how we can know that this graph is not a function. Any function that you write as a graph, the graph has to pass the vertical line test for that graph to actually be a function. Let's take a look maybe at a discrete function. Let's take a look at a discrete function. And again, I'm going to be pretty abstract here. I'm not necessarily going to label the axes. I'm just going to say here is our coordinate plane. And let's draw a discrete function. Let's draw a discrete function. Right, let's draw a discrete function. All right, pretty simple graph. Is this a function, or at least can it be a function? Well, let's see if it's even possible for this function to pass the vertical line test. So we're going to go to any place on the graph where we've actually plotted something, and we're going to draw a vertical line through it and see how many things it intersects. Well, it only intersects this one point here. That's good. A vertical line here would only intersect 1 point. That's what we want. A line here would only intersect 1 point. I'm sure you can see what we're getting at, right? Any point on this graph where we draw a vertical line up and down, it's only going to intersect the function once. And so therefore, any vertical line will only intersect the graph once. So therefore, this graph is actually a representation of a function. What if we had one more data point, let's say right here? Well, that's all it would take to make it so that this were no longer a function, right? Because a vertical line drawn on a graph must only, any vertical line anywhere you draw it on a graph, it can only pass through a data point on the function once. If it passes through any more than, if a vertical line passes through a part of your graph at any more than once in your graph, it is not a function.